large last time, and that's why it died or went out. Okay, so these are our different ligands: strong field, weak field ligands. What makes them strong field or weak field?
Strong field, all electrons are very together.
What do you mean? Yeah, how much they sort of crowd these other spaces. Actually, another mental image that I thought of for this is the ligands are like they're crowding the personal space of the complex ion. And specifically, they're crowding the personal space of the orbitals. As they get closer to those spaces, the electrons don't want to be in there as much because it's crowded. So they're not necessarily in those orbitals. So the electrons, or the ligands that are strong field ligands, they are, this analogy is great, they're all man-spreading. They're just taking up lots of space because they're not doing a great job of holding onto their ligands and like staying in their own bubble. They're just kind of large. So they're not holding onto their electrons, therefore their electrons are just crowding into other people's space. The weak field ligands all are either small or electronegative, or actually, sorry, not small. Some of them are large, like iodine's huge. So either they're large and they can't get close, so they're not crowding the space of those orbitals, or they're highly electronegative and they hold onto their electrons well. They stay in their space. They're not encroaching on other people's seats on the airplane, or leaning over into taking up both of the armrests. The other thing that's easy about this is that all of these, and it's not as apparent in this one, but all of the strong field ligands are nitrogen. So the only strong field ligands you have to remember all have nitrogen. Ene is it's ethylene diamine. So NH2, not CH3, CH2, CH2, NH2. That's what ene is, and it's nitrogens. So all of the strong field ligands are all nitrogen, at least for us in this book. And pretty much everything else is a weak field ligand. So part of what makes these strong field or weak field, the reason that they have these names, is because of how much they split the orbitals. And so I put a little bit more time into adjusting this because there were some things that it was not showing super well. Actually, does it look better in light mode or dark mode? Oh, definitely light mode. Projector's not so good at dark mode. So I made the orbitals different colors, and now it's easier to turn them on and off. The other thing that this was kind of not showing well last time, if you remember, is the orbitals, there was like a line in the middle, which suggests that's like neutral. And whenever we introduce ligands, they would split above and below that. Really, the case is that whenever there are ligands present, they increase the energy of everything. But they increase the energy of the orbitals that they are crowding more. And I really wish I had time to write an assignment related to this. But if you like look at, so let's look at our orbitals here that are like lower in energy. So X, Y, X, Z, and Y, Z. Right? And why are those lower than Z squared and X squared, Y squared? Well, I just put, let's see, let's put, that one's not going to show up very well there. If I put these two orbitals in, that's X squared minus Y squared. That's the higher energy one in purple. Actually, I'll turn that other one off for now. See that the lobes of that orbital are all pointing out at, directly at ligands. But if we look at X, Y, now those are pointed in between, essentially 45 degrees off of each of the ligands. So XY is lower in energy because it's less crowded by the ligands, whereas X squared minus Y squared is pointed directly at those, so it's more crowded by the ligands. And if we turn on, XZ and YZ, essentially look the same as XY, but if you look at it from a different angle. So now we're looking down the x-axis. You can see that those ligands on the top, bottom, left, and right are in between. which is exactly the same as looking from the top down with xy. And so if I look at it here, all of the ligands are in between. If I look at it here, all of the ligands are exactly the same amount of in between, which is why they're the same energy. And if I turn on xz, they'll see that that is also in between in exactly the same way. So this is why crystal field theory predicts that all of these orbitals have exactly the same energy because they're all exactly the same amount of crowded by the ligands. And then the one on here that is a little bit weird is dz squared. I changed this to be the same size, but that's actually not what I want. That's not actually the case. These orbitals all, in theory, have the same volume. And since that volume is spread up between just two lobes and then that donut shape, the dz squared is actually a lot bigger than the other, or looks larger in at least that dimension. Which is why these two, oops, at the same scale have the same energy. So x squared minus y squared is pointed directly at 4 ligands. dz squared is only pointed at 2 ligands, but because it's much larger in those two directions, there's more interference and it ends up being the same energy. So on top of just explaining this again, because this is also the part that kind of got cut out, I did want to look at these examples. So keeping in mind that these orbitals are all affected differently depending on which way they're pointed, and if they're close to ligands, that'll determine if we have splitting or how much splitting we have for our complex ions or coordination compounds. 2, 3, 5. So I got all 5 of my d orbitals. xz, yz, and xy will all be the same. Now, in terms of ligand strength, is chloride a man-spreading ligand? Does it take up extra space? No. Just remember, it's not nitrogen. Nitrogen's all over the place. Can't stay in its own bubble. So we'll have 3 orbitals that are lower in energy. We'll have 2 orbitals that are higher in energy. But the difference between these is going to be relatively small. I say relatively because we're not really putting any amount of energy to it. But what you need to know is if chloride is a ligand that keeps to itself, then the difference in energy levels between my higher energy orbitals and my lower energy orbitals is not going to be that different. The other thing we need to do here is we need to know how many electrons this iron has. So normally it would be, there'd be 6 electrons in its d orbitals. But this is not iron without a charge. This is iron 3+. So it has 3 fewer electrons. So Fe0 would be D6. Fe3+ is D3. Honestly, this feels like kind of a bad example. I guess what's just the question, what's the importance of this splitting? What difference does that make in terms of electrons pairing or not pairing?
Pair with on the bottom as opposed to going to the next level.
They might, depending on the difference in energy. Yeah. So there's basically a fee, there's a tax for pairing electrons. And so it's kind of like the electrons are doing the cost analysis of like, is it worth it to pay that tax to pair with another electron, or would it be better to go by itself into this higher energy orbital? So there's going to be an energy cost of going into that orbital, and you have to compare that to the energy cost of pairing up. Now, we're not going to talk about specific energies, although in some ways that might make it easier. But if this is a ligand that keeps to itself, it's a weak field ligand, this split is small, which means another electron would be more likely to go into its own orbital. It's like if this was so this one's for, move this up. Okay. So let's look at instead, what if this was, because that's for the iron. And what if this was cobalt? So how many cobalt, or how many d orbital electrons does this cobalt have? So on the periodic table, go over to cobalt. Cobalt would be D7, but chlorides have a -1 charge, so 3 minus means that this has to be 3 plus. So this is going to be D4. And we've got the same type of ligands, so we'll have the same sort of small split. So it'll be 1, 2, 3. And because these are weak field ligands, they have less splitting, that electron will go into its own orbital rather than sharing an orbital. So this will be 3 unpaired. This would be 4 unpaired electrons. All right, so if we look at the cobalt, but the hexacyano complex, how many electrons, d orbital electrons, does this cobalt have? So cobalt 0 would be, again, D7. Must be playing through here, huh? Why? Oh, no. So D7, what charge does cyanide have? -1. So 6 cyanides, but I get an overall +2 charge then for cobalt. This is 2 plus 6 minus. So this is going to be 2 fewer electrons. This will be D5. And the cyano complex, it's the splitting going to be for, is going to be small or large for cyanide? Large. Nitrogen, all of the nitrogen compounds are high. So then when I fill in my electrons, I go 1, 2, 3. And I can think about, okay, it's a high spin or high field, high splitting. Means that it's going to take a lot of energy to go into an orbital by itself. So it's better to pair up. So we'll pair those last two. So this would be 1 unpaired electron. So like if you wanted to write these out into steps, you want to know first, is it a strong or weak field ligand? You want to know two, how many d electrons? And three, place electrons in orbitals. If it's high splitting, then you pair them up first before going to the next orbitals. And with the octahedral complexes, those two higher energy orbitals, if I had three more electrons to place, then I would place one here, and then these ones would go into their own first before pairing up. Other complexes do other things, and it depends on, like these are both for octahedrals. So octahedrals have this particular splitting pattern because of where the ligands are. And you can practice drawing those out like in 2 dimensions. If you're going to draw it in 2 dimensions, let's lose my markers. Neither of these are good colors. Nope. So like if I wanted to draw out an octahedral, you just do one of these, Z, X, Y. And if it's an octahedral complex, then I've got a ligand here, ligand here, ligand here, ligand here, one down here. And then you could draw in the different orbitals. So the D, X, Y, D, X, Z, and D, Y, Z, they all go in between. So like if I'm doing D, X, Y, it's going to be on the XY plane. Then I draw my lobes in between those four. Dx squared minus y squared is the one that goes on the lines, x and y. So go here, 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 and then honestly, if you can draw all of those, then when you draw a square planar, you can look at, okay, which orbitals are close to the ligands in square planar. And I would do this along with this sort of simulation. If I switch this to, oh, apparently I broke it. Square planar doesn't work now. Okay, well, figure out why that doesn't work. You can kind of imagine for square planar. Ah. So if we ignore the orbitals on the top and the bottom and the fact that this is actually an octahedral, which orbitals do you think would be the highest in energy? All of them in there at the same time. So x squared minus y squared, is that going to be high in energy for a square planar? Maybe compared to an xy? What about xy compared to x squared minus y squared? might ask. It's for an octahedral. So I'm saying ignore the chart on the right. I wish I could make it not be there right now. Yeah, so ignoring the chart on the right. Huh? Yeah, the one that's dead on, pointed directly at the ligands, will be higher in energy. So the x squared minus y squared will be higher in energy than the xy. Xz is a little bit weird because you have to ignore the ligands. Can I just, no, I probably can't. Ignore the ligands on the top and the bottom for a square planar. So if I only have the ligands on the sides around the equator, how do you think xy, or sorry, xz compares to xy? So xy is kind of in between four ligands. How many ligands are between? Again, ignoring the top and the bottom. Yeah. Because if we ignore the ones on the top and the bottom, then there's only two ligands that are between the orbitals. And same with YZ. So if we're like starting to sort these, we'd expect x squared minus y squared. That's probably going to be pretty high. Below that, dxy, which is the one that points in between four of them, will be below that. dxz and dyz should be the same because they each only have two ligands between two of the lobes. So where does dz squared fit? Again, there's no orbitals, there's no ligands on the top and bottom. Hmm? Yeah, so probably lower than, maybe lower than xy. Definitely lower than x squared minus y squared, which is pointed right at four of them. But maybe higher than xz and yz because it does have this sort of donut that is interacting with all four ligands. That one should be, wow, just smack my watch. dz squared should be somewhere in between. Yeah. So that is the splitting that we see with square planar. It's all just based on like literally kind of counting how many and how close the orbitals are to the ligands. If it's closer to more ligands, then it'll be higher in energy. Tetrahedral is really weird because now we've got everything is coming in off of like major axes. And I haven't programmed that one in yet or spent that much time to look at it, but you should be able to do the same thing. It's still the same idea. Okay, so just some interesting applications of coordination compounds because they get used absolutely everywhere. You're doing it right now. There's coordination compounds inside of you. That sounds weird. Ethylene diamine tetraacetate, EDTA, has 6 lone pairs. And part of the special thing about EDTA is that it's 6 lone pairs that are all spaced out nicely. Oh, I should do this as nitrogen, and then each of these has a CH2, and then a C with a double bond O, and then an O. That's a lone pair. And then one more of those. And there's lone pairs here, there's lone pairs here. And that thing just kind of like flies out and then just hooks onto metal ions. It gets used for heavy metal poisoning. So you use calcium EDTA. So there's a calcium ion that goes into the middle, but that calcium ion is not as stable inside of that as heavy metals are, so like lead. And actually one of the reasons that lead and like arsenic are so toxic is because they replace calcium in the body, because they end up being more stable in those situations. So especially lead 2 plus, arsenic 2 plus, arsenic 2 plus, because it could be a 2 plus. But those ligands, they fit into and mess with other places where calcium gets used. Oh, no. Arsenic replaces phosphorus. That's what it was. But like the calcium gets bumped out by the lead, and the lead being actually a much larger ion fits better into that ligand. And essentially the chelation is giving, well, for one, it's preventing the lead from then going and replacing calcium. But it also gives your body some handles. This EDTA ligand acts basically as a handle for your body to remove the lead. Chemical analysis, which if you used the either have or will today use the iron or the thiocyanate to check for iron. So you get different colors. You can use it as tests for those metals. It can be used in different coloring agents. There's a lot of places where we use these sort of synthetic ligands. But biomolecules also use complex ions. So hemoglobin and cytochrome C are both contain a heme. So it's using iron and a porphyrin, which is this big ring on the right. The ring around the outside is the porphyrin. And so that coordinates to the metal, and then that metal can coordinate with oxygen or other things. And then iron is, or the heme, has a square planar arrangement of those nitrogens that holds the iron in place. And on either side, or then a nitrogen on the others, which we can't see would be in the plane. And then oxygen compared to the other side. And then when it doesn't have oxygen, it's water. Another enzyme that uses zinc in a tetrahedral complex, carbonic anhydrase, and then chlorophyll, which is also a porphyrin, which I think is interesting because the chlorophyll kind of does the opposite of, or it doesn't do the opposite, right? We respirate and we turn oxygen into CO2 essentially, and then plants are taking CO2 and turning it into oxygen. And it's kind of the same complex that does this. There's a really, I haven't found the video, I can share it yet. Oh, we're not gonna have much time. Rubisco is a enzyme that's in plants that is just really bad at its job. And so plants express a ton of it. And there's been a ton of research into if we could make Rubisco better, because it's not very selective, so it picks up the wrong stuff all the time and then breaks, and then the plant has to make more of it. And sometimes it just drops the things that it's, like it'll capture CO2 and it just drops it. It's just really, it's really bad, but nobody's been able to figure out how to make it better. Because if you could make this thing, this Rubisco, better, then you could massively improve the efficiency of plants. Because they're wasting tons of energy just making more Rubisco for it to do its job badly and fall apart. Yeah. I saw this morning and I was like, was it chlorophyll? No, it's Rubisco. But they say that there has been, like, some plants are evolving like better efficiencies for Rubisco. It's just really, really slow. Okay, that doesn't leave us a ton of time, but